Yeah, let's talk about the book. So we read chapters 1 and 2. Usually the format we go for is that Justin will sort of talk about the chapter a little bit, and we ask questions. So cool. Want to just switch over and talk about the book, Justin?
Okay, a couple thoughts. Firstly, I'd like to sort of normalize lack of preparation. I have the benefit now of having sort of gone through my stuff once, but all the implementation stuff you haven't. So, you now get to experience all of the hiccups that you know uh, I did last time. There is some suggestions. I'm happy to do the book first. I guess there's some suggestions in the chat about some things that might be useful that look like they could be figured out maybe on the fly. If I don't know, we could open the floor briefly to just if anyone wants to raise specific issues they encountered and how they got around them, or I could just start with the book stuff, and that buys time sort of to ponder how to proceed with the implementation stuff. What are your thoughts based on that?
Yeah, sure. If anyone would like to raise their hand and talk about their implementation, I think that would be useful. I think it would be a sage asked, would it be possible to flag the best implementation so we can reference it? Yeah, I could definitely do that. I think it would be something that I should probably do after this session because randomly reading through your repos and saying, I think that's real good, seems like the wrong way to do that. Um, and yeah. So if anyone got stuck on anything in their implementation, raise your hand, or if you'd like to talk about your implementation in particular, raise hand and we can bring you up.
Okay, in 15 seconds, I'll just move on to the book thing, and then we can think further about what the implementations. And I also think that with implementations, maybe the best way to approach it could change as the protocols get vastly more complicated in like Friedwald's algorithm. Like back when I was implementing things myself in grad school, I would just write in C, and all the modular arithmetic, it would just be like matrix vector multiplication. That would be the protocol, like of almost like a 5-line program, and then all the modular, other code bases and stuff. And it might be making the simpler things much harder to get out the door, but then making the more complicated things more usable and better is sort of my impression, just sort of looking at glancing at what's going on in the chat. Anyway, so did anyone want to speak?
Yeah, I think we've invited Shell back up to ask a question. Hey, Shellback, what's your question? We can't quite hear you. Maybe check your mic setup.
Do you hear me?
Yeah, I can hear you now.
Do you hear me?
Yes.
You hear? Oh yeah, good. Now it's okay. So I don't have implementation, but following the comment in the channel, and then I saw this heated discussion. Actually, it's related to what Justin says about the matrix multiplication, and then some people said just go implement it yourself. And I was wondering if there was a winner of linear algebra library that people thought is the best for the task between everybody who used it. So it's more of a question in general that what people end up using for linear algebra of that type.
Yeah, so in the implementations I saw that were submitted, it looked like most people were either implementing their own matrix implementation, or they were using NAlgebra's library, which is a REST library that I think is sort of used by a bunch of different fairly high production orgs. So yeah.
And algebra.
Yeah, NAlgebra.
Okay, thank you.
Which Gray posted about in the comments. Any other questions before we sort of move on to, okay, so let's loop.
Can you guys?
Hello.
Okay, cool. I have like one comment that can be like maybe we can.
It's a little bit tricky to hear you. Could you maybe move closer to your mic?
Is it better now?
Yeah, it seems better.
Okay, so I just had like one comment about like what we can do. For instance, while generating a random field element in Rust, I struggled a while because like the current tutorial online was, I guess, outdated, or like it required us to like compile the actual repository, which I have actually seen from the chat. So and it kind of helped a lot. So I guess what we can do is like we can create these like updates to the actual repositories, right? Like artworks, and then maybe we can submit them to the maintainers, or can like directly edit their documents to make it more updated along the way. Because I feel like we're gonna figure out like many things that have been like deprecated or like not updated in the long run. So I just wanted to.
Yeah, I suppose that's sort of especially a good point because it's one thing when you discover that a library is doing something wrong by yourself and then you just move on. But it's another thing when a bunch of people discover your library is doing something wrong and then you feel embarrassed and like encouraged to fix it. So I think that's like an interesting social dynamic observation that we could probably help library maintainers to like keep their library up to date.
Yeah, exactly.
Cool. That's a good thought. Yeah.
Thank
you. Let's see. Oop.
Hello, hello.
Hello, hello.
Hey, yeah, just a general comment. So I actually started implementing the algorithm as a binary in Rust. Like I just wanted to have a nice CLI interface, and just it's not worth it. I think it's much better to do it as a library and just write some tests. And while a binary might be better for kind of playing with it, you can still do pretty good with just the lib, and it'll just save time for kind of parsing any sort of inputs that you want to provide for a CLI. Just a general comment for future implementations.
Okay.
Yeah. And yeah, regarding ArcWorks, so I'm actually a contributor there, and any pushes are welcome. Especially like exactly if you find stuff that doesn't work, or a tutorial that needs to be updated, or any code comments or anything, just make a pull request. That'd be great. Thanks.
Cool. Awesome. Let's see one more.
Hey, thank you. I just had one question, Jason, about ArcWorks. So one of the hardest things was I couldn't make any use of the serialization, canonical serialization stuff. So I had to do kind of my own serialization. So any guidance on that would be super useful as we go forward and try to implement this stuff.
I don't think anyone's going to stand up for the serialization implementations at this particular moment, but that might be something to look into further. So assuming that there are no more questions, I think it might be good to go talk about the book. Does that sound good with, I suppose, my asking questions, does that sound good no longer really makes sense? Since I think like the only interface to respond to them is in the chat. So yeah, let's move on to talking about the book for today. So we read section 3.1 through 3.4, sort of ending with Schwartz-Zippel, which was sort of like a lot of like definitions and preliminaries. Want to sort of introduce this section, Justin?
Sure. Actually, I'd like to start briefly with some comments about last week's reading and some updates I made in light of the questions and confusion that came up last week and in the chat, I guess. And yeah, I suppose if you'd like to type any questions you have as I'm speaking in the chat, I'll be watching it just now that you can't just unmute yourself, I guess. Yeah, so I think the biggest source of confusion that's come up repeatedly, which I did address last week and has been addressed a bunch in the chat now, but just to repeat for anyone who wasn't here and missed it, I guess, was the treatment of Reed-Solomon codes in section 2, which were sort of, it was just mentioned that in the fingerprinting communication protocol, what Alice and Bob were doing, one way of viewing it is they were both sort of in their own heads taking their vectors and thinking about the Reed-Solomon encoding of these vectors. So that's taking these vectors and sort of blowing them up into much, much bigger vectors. And the Reed-Solomon encoding procedure is distance amplifying, which means any two vectors that differ in even a single coordinate, their encodings differ almost everywhere, right? And then the Alice and Bob were then just picking a random entry of the encodings and just comparing that one entry of the encodings. And because of this distance amplification property of Reed-Solomon codes, right, if their vectors were not the same to begin with, then when they compare just a single randomly chosen entry of the encodings, it would pick up on the inequality, the vector inequality. So even one coordinate difference would get picked up with high probability. And so, yeah, a big source of confusion was me calling that an error correcting code. And just to clarify, in these protocols throughout the book, they frequently use what the literature calls error correcting codes, but no one is doing error correction, right? The only property of the encodings being used is the distance amplification property. And it turns out that distance amplification is sort of enough to let, to correct errors in the encoded vectors if they, popped up. But like that, you can forget about error correction for purposes of the entire book. So yeah, I added a section in at the end of chapter 2 to sort of cover what I just said, in a self-contained way. And I'm going to go back and sort of make the comment or eliminate the word error correcting code, push it to a footnote or something, because it has rightly generated a lot of confusion about, who's correcting errors, what are these errors? No one in the protocols are correcting any errors. Okay, and just since as I make changes, I think it's worth telling you about them. So if you go and download the update, you're not shocked. I also changed the definition of Reed-Solomon codes of the fingerprinting protocol in the book. Before the Alice and Bob were interpreting their vectors as coefficients of polynomials, where I had the coefficients being like, the first entry of the vector was the degree 1 coefficient, the second was the degree 2, the third was the degree 3 coefficient. And that meant the polynomials just had no constant term. And I was doing that, it wasn't really a great reason. It slightly simplified the notation in the chapter. But like the standard convention is actually for Reed-Solomon codes is for those polynomials to have, non-zero constant terms, meaning, actually the first entry of the vector is like the degree 0 coefficient, the second entry is the degree 1, the third entry is the degree 2 coefficient. And so I changed that, and it doesn't really change anything about the soundness, and everything's basically the same. It just the indexing in the book just has to change ever so slightly. And I did that change because when I added the new section on Reed-Solomon codes to the end of chapter 2, I now put in a picture of, here are some vectors in their Reed-Solomon encodings, and it looks so weird and non-standard to to do things that the way I was doing before with no constant coefficient. So for those who implemented Friedwald's algorithm, like as described in the book, well, now the description has changed, but in sort of this totally inconsequential way. Hopefully that made sense. And then the last change I made was for the reading for this coming week, it will cover low degree extension polynomials and multilinear Lagrange interpolation. And I reordered the coverage in that section because I got some comments which are super helpful in the chat that the current coverage was confusing because of the ordering and stuff. So anyone who hasn't read that yet, you might want to update the book. I think it's a little bit improved now, thanks to your feedback. And just one thing I want to do this coming week is in this new section on Reed-Solomon codes, I'm planning to add coverage of what's called univariate polynomial interpolation. This isn't, you don't need to know this for anything in the book for a very long time. So I just want to flag that that's going to go in there. And the reason it's going to go in there is so that when you do encounter multilinear, Lagrange interpolation for multilinear polynomials in this coming reading, I think it's helpful to have seen the univariate version first. So future readers, unfortunately not the group here, but future readers will have the benefits of seeing univariate Lagrange interpolation before they see multilinear Lagrange interpolation. So these are like the pros and cons of you reading the book now is based on your feedback. It gets much better, but the downside is if you just waited a month or something, you would have the benefit of the improvements as you were reading it the first time. Anyway, okay, so with that out of the way, so the reading for today just introduced the notions of interactive proofs and arguments, I think the best thing to do with that, rather than summarize what they are, is just open the floor for questions in a minute. Because hopefully the way they were introduced just made sense, but probably there was things that were confusing. There was also a bunch of discussion about what I call robustness of the models. That basically means there are a lot of small choices you have to make when defining the models. Things like, are the protocols public coin or private coin? The book has discussion about what that means, but basically, in a private coin protocol, the verifier can toss some random, make random choices, right? And keep that randomness hidden from the prover. That's private coin. Whereas in a public coin protocol, every time the verifier tosses a new random coin, the prover, it's that toss is done in public. The prover immediately sees that value. And in these public coin protocols, in fact, it turns out to be without loss of generality, that the only sort of messages from verifier to prover are these coin tosses. The verifier doesn't have to send anything else to the prover. So you kind of have the choice of how you define the model. Is it public coin or private coin? And the book talks about how the choice really doesn't matter, in principle, because there are known transformations. You can take any private coin interactive proof and turn it into a public coin one, and roughly more or less preserve the efficiency of the verifier. Now, there are caveats here because it doesn't exactly preserve the efficiency of the verifier, right? If you take a private coin protocol and you apply this transformation to turn it into a public coin one, the verifier will get slower and the proofs will get longer, but the verifier won't get that much slower and the proofs won't get that much longer. The prover might get vastly slower when you go from, when you transform the private coin one into a public coin one. So the chapter talks about these, tells you that these transformations exist, they're known. But you wouldn't actually want to use them in practice. The way we design the snarks, that people are using today, is not to first design a private coin protocol and then transform it into a public coin one, right? And then apply the nice transformations we have for public coin protocols to get a snark. Instead, it's just the natural snarks. They're naturally public coin. So it's kind of a weird thing, which hopefully the chapter covered in an understandable way, where these transformations, from private coin to public coin and all, imperfect completeness to perfect completeness, and the chapter just went through a bunch of things. It's good to know these transformations exist, and they kind of tell you, as you're deciding exactly how to define the model, it sort of doesn't really matter what choices you make. Because if you make one choice, you can always take a protocol for that model and transform it into one had you define the model with an alternate choice, and the costs are roughly preserved. But basically, all of the natural protocols in these models sort of naturally have the nice properties we want of being public coin, of being perfectly complete, which means an honest prover will always convince the verifier to accept. The honest prover is in these protocols is always naturally deterministic. Now that will change once zero knowledge comes into the picture, because to achieve zero knowledge, the prover sort of has to act in a sort of random manner to avoid leaking any information to the verifier about, the witness that the prover has in its head. So yeah, there was a bunch of stuff in the chapter about the models and discussion about how these really the 10 different low-level choices you might have to make to finalize the model ultimately don't really matter that much. And then the last thing that was assigned was the Schwartz-Zippel lemma, and this is just a statement that says if you take any two multivariate polynomials that are both low degree and you evaluate them both at a random point, okay, then with high probability, if they're not the same polynomial, with high probability over that random evaluation point, they're going to disagree at that point. And another way to say that is that any two distinct low degree polynomials can only agree at a very small fraction of points of inputs. And the univariate version of the Schwartz-Zippel lemma is really just like the fundamental theorem of algebra. It's just the statement that like a univariate polynomial of degree at most n has at most n roots. That is n inputs where it evaluates to zero. So it's actually a pet peeve of like some folks to use, say Schwartz-Zippel in the setting of univariate polynomials, because it's really like the fundamental theorem of algebra then. But people do it anyway, so I don't know. You probably shouldn't worry that it's a pet peeve. But yeah, if you wanted to be careful, like when you apply, the univariate version of Schwartz-Zippel, you shouldn't call it Schwartz-Zippel because it's much simpler in that case. Okay, so that was my rambling summary of the reading for today. And yeah, I guess I'll just open it for questions.
Just a quick comment about private coin to public coin protocols. I found a paper discussing the transformation from private coin to public coin systems, but if anyone has either a sort of higher level resource, the paper that I found maybe is a little bit more in the weeds than probably a simpler discussion. So if anyone has any better resources or simpler resources than that, they're welcome.
Yeah, I'll say that paper looks like it's focusing on this question in the context of zero knowledge proofs. So which is great. In the reading, chapter 3, the book hasn't really introduced zero knowledge formally yet. So the transformations it's referring to there are for non-zero knowledge, interactive proofs. And then things are simpler, like that results dates back to the mid 80s, like not very long after interactive proofs were introduced. And yeah, I'm trying to think what's the best. I'll have to think offline about if anyone's interested in details of that transformation. What's the best thing to read? I could also sketch it verbally, but it's not trivial. It's not it's not like the most complicated result ever. But like, yeah, there's cleverness in the transformation for sure. Do I want to say anything else? Maybe that was it. I lost my train of thought because I was very sleep deprived. Yeah, okay. Any other questions?
Oh, so follow up on that. What exactly is causing the polynomial blow up when we're going from a public coin interactive proof system? Sorry, when we're going from a private coin interactive proof system to a public one?
Yeah, great. So I guess I can't really answer that question without sketching how the transformation works, which I'm happy to do. So let me try to remember this off the top of my head. Okay, yeah. So the transformation takes the following view of a private coin protocol, and I see questions coming up in the chat, so I'll read them after I try to answer this. So with the private coin interactive proof, there are sort of two situations you can be in. So one is where the prover is making a valid claim, and the other is where the prover is making a false claim, right? And completeness and soundness of the interactive proof system require that in the former case, the probability the verifier will accept, like the honest provers are, answers to the challenges is high, say very close to 1. And if it's perfect completeness, it's exactly 1. And in the latter case, where the claim is false, the probability over the verifier's sort of random choices, private random coins, that the prover convinces the verifier to accept is very low, say close to 0. So you have two different situations, like in one, and one of them has to be the case, right? Either the fraction of private coins of the verifier, the random choices that will cause the verifier to accept the prover's responses is large, or it's small. It can't be in the middle. Okay, so what Goldwasser and Sipser do, because that's the authors who came up with the transformation, is they come up with a public coin protocol to show that a set is large. So the set at play here is like the random choices that the private coin verifier might make that lead to like acceptance of the prover's messages. And let me see if I can say a sentence about how the prover proves the set is large. So the idea here is like the verifier would randomly choose a hash function mapping private coin values to some range, and if the set is and then says to the prover, hey prover, like tell me here's a possible output of that hash function, tell me a pre-image in the set of that value. So that is, tell me a setting of my private coins that would cause me to accept like your responses to my challenges, and moreover would hash to this particular value, right? And if the set is big, then like with high probability, there's like some pre-image of that particular random value, just because there are a lot of things getting randomly hashed. Whereas if the set is small, then with with decent probability, there won't be any pre-image, just because there are very few things that you could try to hash. And so the prover would have to get pretty lucky for something in the small set to hash to that particular value. Okay, so that's the public coin protocol, like at a very high level, that comes out of that the private coin one gets transformed into. So there's a lot of overhead here. So for the prover's perspective, the overhead is enormous, because now it has to like find a pre-image under this hash function within this particular set of private coin tosses that would have led to acceptance. And that could be, I guess, potentially, these aren't actually cryptographic hash functions, so you don't have to like invert a cryptographic hash function, but still that could be a difficult computational task. And that, from the verifier's perspective, right, like now, it has to like do extra hashing, that it wasn't doing before. And you can just see how the verifier in the resulting public coin protocol is just doing more stuff than it necessarily had to do in the original private coin protocol. Like it's choosing a random hash function, sending it to the prover. The prover says, hey, here's like the pre-image you're asking for. The verifier has to actually then apply the hash function to the claim pre-image to confirm it is indeed a pre-image. So yeah, maybe that gave you some idea. It was a much more meal of a question than you probably thought you were getting into. Yeah.
That's really helpful as a guideline to dig in more. Thank you.
There's quite polynomial blowout means end of the k, right? For some k greater than 0. Yeah, that's what it means. So whenever the book says like a polynomial blow up or polynomial anything, what that means is if n is like a measure of the size of the input to the computation of interest, polynomial means n to some constant power, whether that constant is 1, 2, 3, whatever. Just some number that doesn't grow with n. So n squared is polynomial, but like n to the log n is not, because log n grows with n, however slowly. So polynomial blow up in the verifier's costs mean, if in the original protocol the verifier ran in time order n, then in the transformed protocol the verifier might run in time n squared or something like that. So theorists consider like a polynomial blow up to be sort of acceptable, like, not that big a blow up, but like in practice, going from n to n squared is terrible. So we'd really like like a linear blowup, meaning like just a constant factor, or at worst like a quasi-linear blowup, which means like a factor of you get an extra factor of log n in the verifier's runtime that wasn't there before, or something like that. Okay. I'll just read this question that I think Thor answered. Is the measure of S or F or just the number of elements in the finite field? I don't remember what S refers to. But yeah, outside, if I put, if I have like, what looks like absolute value of field, that notation in the book, that means the number of elements in the field. Yeah. So I guess I'll have to go back to the book where I first used that notation and make sure I make that clear. But like absolute value of some finite field, that's referring to the size of the field. Oh, and the short Zippo lemma. Yeah, and that lemma, that must be how it's used. I'll pull it up as I mute myself. But yeah, that means size of the field. Let's see. Just pulled it up. Oh, I see. Okay. Sorry. Okay, now I have the lemma up in front of me. That's where S is coming from. Okay, so whenever we apply the short Zippo lemma I don't want to say whenever, almost always when we apply the short Zippo lemma, like with maybe like one little exception, the set S in the lemma statement in the book will be the entire field. But the lemma is stated a little more generally to say, what if the verifier like didn't evaluate the polynomial at a point randomly chosen from the whole field, to the number of variables of the polynomial, but just like a subset of the field. So I don't. There are certain situations where, for whatever reason, you really want the verifier's evaluation to be limited to some like special structured subset of the field. This comes up in some what are called IOPs, which we don't discuss till like chapter 10 or something. And in that case, the lemma is still giving you a bound, as stated in the book. So yeah, but absolute value of S, what that really means is size of S. So I will go back and clarify. Thank you for the question. In the statement of the lemma in the book, that notation means the size of the set S. Yeah. And sorry for taking like 2 minutes to answer such a simple question. While people might ask more questions, I'll say the reading for, I guess, next week, which will be, I guess, the rest of chapter 3, just discussing low degree and multilinear polynomial extensions, and then the start of chapter 4. We're going to start seeing like our first interactive proofs. So like this week, the reading was like really dry, and maybe that's why there are not so many questions. It was just introducing the key models. It's probably the most boring reading sort of the entire book, but obviously it's important. And so, I find it exciting to, we sort of dive right in section 4.1 into like my favorite interactive proof and the most important one. The next week might be a little more interesting. Yeah, let's see. We're getting close to done. If there's just not that much to discuss this week, but there's some typing going on, so I'll just mute myself.
I have another question. Can you talk more about language problems? And can we say that they are a subset of functions?
Yeah, great. So what I would say is giving an interactive proof for a language is in some sense like strictly easier than giving it for, like the natural definition of a function corresponding to the language. Okay, so let me elaborate on that. So with a language is just like, you could think of it as a function, but this is where you're going to get into trouble. You could think of it as a function where the output is always either yes or no. And an interactive proof for a language requires only that yes instances have convincing proofs of their yesness. It does not require that no instances have convincing proofs of their no-ness. And the reason people defined interactive proofs in this way for languages is they were thinking of yes instances for the language as like the set of all true statements, all valid statements, and no instances, it's everything else, the set of all false statements. And under that way of thinking about things, it's very natural to say, well, like in a proof system for the language, like all true statements should have convincing proofs of their trueness, and false statements just should not have convincing proofs, right? Because that the prover shouldn't be able to convince the verifier of the validity of a false statement, right? That's not valid. So that's why people define interactive proofs for languages in that manner, in this sort of asymmetric way. Again, yes instances need to have convincing proofs of their yesness. No instances do not need convincing proofs of their no-ness. It's just required that there not be convincing proofs of their yesness because they're not yes. Whereas for functions, where for many functions like that you would care about, the output is not just yes or no. You might be what's an example? I mean, almost anything you can think of. Matrix multiplication, right? You're taking two matrices, you're multiplying them, right? The output is a matrix, right? It's not yes or no. It's natural that whatever the correct answer is, you're going to require that there's a convincing proof that the answer is correct. So that's why there's this discussion in the book about languages versus functions, and it feels very pedantic and might not be the clearest, which is why you're asking about it. But why I felt I had to have some discussion, and maybe I'll come up with a way to make it clearer in light of this rambling response. And so the last thing, there is one sentence in the book that points out that you can phrase the task of giving an interactive proof for a function as the task of giving an interactive proof for a related language, but the converse is not true because of what I said before. Like, giving an interactive proof for a language is not. It might be strictly easier than giving an interactive proof for like the yes/no valued function corresponding to that language. Again, the difference being that no instances do not require convincing proofs of their no-ness if you're dealing with languages. So it's sort of only a one-way equivalence, right? Like, to give an interactive proof for a function, there's like some language that it's equivalent to giving an interactive proof for that language, but to give an interactive proof for a given language, there's not a particular function where it's giving an interactive proof for the language is equivalent to giving an interactive proof for the function. Okay, so I'm done rambling. I hope that was helpful. Let me know if you have follow-up questions.
That was helpful. No follow-up questions.
Great. Okay, so I'll look at the chat now. Thanks. Okay. So the response to the question about x arrow s to the m is correct. So that notation means x is chosen like uniformly at random from the set, s times s times s, m times. So I'll clarify that. Thank you for the question. Question that I asked last week about soundness. We have right. Okay, so the question now is, last week I said if you had an interactive proof and you required that the soundness error be 0, meaning like there's no way for the prover to ever get lucky and convince the verifier, to accept an invalid statement. I said you'd wind up with only the power of NP, which captures like static, non-interactive proofs. So I said, like, you really need to combine interaction with randomness, non-zero soundness error to get like a more powerful kind of object. And the question now is, when we apply Schwartz-Zippel or, the univariate version of it in some situations, it sort of says that any two distinct polynomials can agree at most n points. So if you confirm without a doubt that they agree at n plus 1 point, like deterministically, they must be the same polynomial. Isn't that enough? I would say that the issue in the context of interactive proofs is not just that that's inefficient. And in fact, in interactive proofs, we wind up using multivariate polynomials where actually the degree is like very small relative to the size of the input that we're dealing with in the interactive proof. It's actually just logarithmic. So actually like querying like a polynomial at the necessary number of points for this question to sort of make sense is not super inefficient. It's more than we would like because it's more than one, but it's only logarithmic in the input size. That's not so bad. Again, like log of a billion is just 30, right? So the real issue is the following. In an interactive proof, these proofs are sort of ephemeral in a sense. Like basically, it's not like if the prover like sends, how do I say this? Like in any one run of the interaction, the verifier is only going to be able to like query the polynomial at one point to like make the prover sort of tell it the evaluation of the polynomial at one point. This won't make so much sense until like next week, basically, when we talk about the sum check protocol. But yeah, that's roughly the case. It's something like that. In any run of the interactive proof, the verifier can kind of only get one evaluation of the polynomial. I'm waving my hands a little bit here, but so if you want, if you wanted to get more than that, you kind of have to run the protocol again, one for each evaluation, if you will. But then every time you run the protocol again, the prover can change the polynomial that it's sending. So like you literally just can never get enough evaluations of the same polynomial to drive that soundness error to 0 in the manner you're suggesting. So this is a very hand-wavy response to your answer, to your question, because we haven't actually seen these interactive proofs yet to give a precise explanation. But that's the rough idea. So with these interactive proofs, like the best you can do often, there's kind of going to be two ways to drive down the soundness error in these interactive proofs. One is typically going to be to just increase the size of the field you work over. Because Short-Zipple says, you evaluate a polynomial at like a random point and the probability, it's 0 or, agrees with some other different polynomial at that point is like degree over field size. So you make that field bigger, that kind of probability of the bad event goes down. So that's always one way to drive the soundness error down, is to make the field bigger. The other way is to just repeat the protocol like independently many times. And in the interactive proof setting, it actually turns you can do it in parallel, and that way you're not blowing up the round complexity. So you can actually run the protocol like 1,000 times, like in parallel, like kind of stepping each protocol forward one round at once, and that will cause the soundness error to fall down from whatever it was, say 1/3 to 1/3 to the 1,000. You do have to get careful about parallel repetition in other settings like zero knowledge and stuff. We don't have to get into that right now. If you want to make 100% sure you avoid any like really subtle issues in all possible scenarios with interactive proofs and arguments and multi-prover interactive proofs and stuff, you would do the repetition sequentially. So you like run the protocol once, right? Like that might have soundness error 1/3. If you run it a second time and you only accept if like the verifier in both instances accepts, right, you'll drive the soundness error down from a 1/3 to a 1/9, right? So basically, like the prover has to get lucky twice instead of once. But the point is, no matter how many times you repeat it, you're never going to get that soundness error all the way down to 0. Okay, so as always, rambling response, but I hope it's helpful in the end. Cool. I actually don't see typing. Anyone have more questions? I mean, so maybe I'll just, so thanks again for both the questions, especially stuff that isn't clear, because that's like immediately improves the text. And yeah, just anyone who, I'm interested in more feedback on the multilinear polynomial extensions coverage, because it's quite technical, and you can't really see why it's so useful until the next chapter when we cover the sum check protocol. So it's maybe the part of the book that I'm like sort of most worried about. It just kind of feeling very technical and difficult when in fact it shouldn't be. And yeah, if anyone sort of just wants to wait like several days, I'm hoping to again put in coverage of like univariate polynomial, like Lagrange interpolation and univariate low degree extensions inserted to the very end of chapter 2, which could potentially make the covering the multilinear version of all that a little less I don't know what the right word is, but like jarring. So yeah, I don't know, maybe give it a try earlier if you can, and if it's rough, hopefully by the end of the weekend, there might be a slightly gentler path forward. Yeah. Okay. Yeah, of course. Happy. I thank you for your efforts going through the how rough it is. I do also. I think the later chapters might be a little more polished. Kind of counterintuitively, the simpler stuff sort of becomes more of an afterthought because you're less worried about it. Then it turns out that there's more embarrassing, unclear stuff in the earlier chapters. Are we going to talk about pairings? We will talk about pairings for sure. That they're not covered till much later in the book. Actually, Thor at some point I think might raise the following question. The book is kind of organized in two parts, more or less. Sort of the beginning of the first half of the book is kind of covering the information theoretically secure protocols. Right, because snarks, they always have like an information theoretic component and a cryptographic component. So the first half of the book is covering the information theoretic component, and that's where like short Zipple and stuff is exploited all over the place. And then the second half of the book covers the cryptographic component. So naturally, pairing-based cryptography comes up in the second half of the book. And so we kind of have an option of the path through the book.
Just to preface here, I'm going to put up several polls at the end of this session. So one of the polls is going to be directionally, would we like to hit the information theoretic component before we sort of hit the zero knowledge component? Or we would like to do that in the opposite order. The last group that we went through, we sort of just touched on the sum check protocol here in chapter 4 before jumping on to chapter 7 to hit Pedersen commitments, and then jumping on slightly later to the book to really hit like the zero knowledge amendments to information theoretically secure protocols. So Justin, you can take back over. So I'll put up a poll here at the end of the session that you can sort of vote on whether you would like to hit protocols first or ZK first. And I think I probably know which way it's going to go, but.
Yeah, sounds good. Yeah. So yeah, to just elaborate, that's great, Thor. To just elaborate, like one sentence on that. So like, yeah, so to cover the cryptographic components of these snarks, like it's really helpful to know I think you have to know a little bit about the information theoretic components, because the whole point of the cryptographic components is to take those information theoretic components and transform them into snarks. But and this was like the approach we took, with the previous group. You don't have to know that much about the information theoretic components. So it's sort of enough to like read the first 2 sections of chapter 4 and maybe the last section of chapter 4, or and then and then you're sort of off to the races. Once you sort of cover like one information theoretically secure protocol, and that's enough to then jump forward to the cryptographic stuff. So my guess is that is how people will want to do it, but the poll will be helpful. So and these aren't mutually exclusive. It's just a question of the order. So we can obviously go very deep into the information theoretic stuff, and that means like essentially going linearly through the book. And it just means you don't get to any of the cryptographic stuff until it's like chapter like 11 or something. So anyway, that's the point of the poll. I think that's everything I had to say this week. Last chance for questions. Okay. Thora, is there any wrap up? Or should we just call it a week?
I do see a hand, so I'm going to pull that up before I do.
Sorry, there was a question about the exercise, no, the assignment, and maybe I missed your answer. There is a question that says when is the next coding assignment? What is it?
Yeah. So the next coding assignment is going to be implementing specifically the Lagrange algorithms at the end of chapter 3, which is presented in section 3.5. So lemmas 3.7 and 3.8 are going to be recommended implementation exercises. That's frankly going to be more along the lines of something similar to the Lagrange implementation. So if you'd like to skip that, the next like major protocol that you're going to be implementing, or actually the first major protocol you're going to be implementing, is in section 4.1, and it's the sum check protocol. So for like total homework, implement lemmas 3.7 and 3.8. and implement some check. But I don't think we're going to get to that until not next week, but 2 weeks from now. But we can start talking about implementations either next Wednesday in our sort of informal session, or if there's extra time at the end of next Friday, we can start talking about that too.
Thank you.
Yeah, and it's a shame that I didn't put in already the univariate Lagrange interpolation, because that could be a nice coding exercise too. But again, hoping by the end of the weekend or something that goes in there.
Yeah, so as far as organization stuff, I'm going to post several polls in the chat here when the group ends. And I think next week we should look to be reading the rest of 3. And I think the sane thing to do would be to read the rest of 3 and the first section in 4, so 3.5 and 4.1. 3.5 has 2 decent coding assignments, like I just said, at the very end. And section 4.1 is the sumcheck protocol, which is sort of the heavy lifting gear in the GKR protocol, which underlies a lot of linear, what is it? Linear IOPs or linear, what's the word? PCPs, linear PCPs. Isn't that right, Justin? I think that's correct.
Not linear PCPs, but polynomial IOPs. I guess you could put it that way. Yeah. That is unfortunate. You got linear PCPs and polynomial IOPs, and they really need to be distinguished. But they sound it's a lot of words. Yeah. Okay. That sounded like everything to me.
Okay. Cool. So I think I'm going to post several polls. The first poll is going to be about the group pace, whether it's too fast, just right, or too slow. We're sort of going over some of the easier material right now, so we're kind of stepping right along. But as we sort of hit some of the more like cryptographically interesting and slightly harder material, we might want to slow the group down a little bit. But I suspect that the group pace right now feels a little bit easy, so expect it to get a little bit harder as we get deeper in the book. The second poll is going to be about which topics you would like to approach first, specifically the information theoretic components of the book. So basically choosing between the information theoretic chapters, which are sort of like the center of the book, like 5 through 10, and the more cryptography components of the book, sort of starting with Pedersen commitments, and then using the GKR protocol to sort of implement polynomial IOPs and linear PCPs, stuff like pairing schemes and bulletproofs kind of come out of that too. And then I think the third poll is going to be specifically about how the group would like to do coding and implementation weeks, so that I can sort of get a sense of how to maybe prepare for the next implementation week. That's it.
Yeah. And I think there's a question about a written schedule anywhere. I think the answer right now is definitely no. In particular, in terms of like what we're covering week by week, in particular, the polls are going to inform that. Maybe you just meant when people meet, which is a question for Thor.
All right, cool. So let's wrap up. Thanks everyone for coming, and see you again next week.
Thanks everyone. Have a great weekend.